So our presenters, Kurt Breitenbucher is a registered professional engineer with 11 years of experience. He received a BS in civil engineering and a master's of science of geotech engineering from Michigan Tech. Primarily works in trenchless projects, tunnels, and supports excavations across the country. Based here in Minneapolis, he's been with Brierley for about 7 years. Sam Umlauf started his career in the construction industry working as a field inspection intern in central Wisconsin. After stops in California and North Dakota, he settled in Engineering and Construction Innovations, Inc. at the end of 2014. His focuses while at ECI have been design and construction of specialty geotechnical, marine, and tunnel projects with a basic intro to soil mechanics as his only formal, quote, classroom geotechnical education. Sam's geotechnical and geostructural expertise has primarily involved rolled up sleeves and dirty hands. So here, guys, please give it up for Kurt and Sam. Oh yeah, and I forgot, last month we had some problems with the PDH thing, so there are printed out PDHs, so don't forget those when you leave. If you do, because you're like my 6-year-old, email us and we will send you them, but preferably grab these. All right, so they use this and these.
They can, yeah. And then, yeah,
If you'd like to take both, because one is this one, this one's for virtual, for the people online.
Yeah, oh.
So we're gonna clip that one for sure, and then if you want to yell, you can yell. If you want to use that one and
yell.
not yell, go for it.
I can yell. That's good by me.
Okay. Put this here. Nothing.
I don't know how anybody's gonna say if it's working. Okay.
You want to give your
All right.
quick spiel?
Sam again with ECI, Engineering Construction Innovations. We're a specialty heavy civil contractor based here in the Twin Cities. We do work all over the country, really. Company is owned by Shane McFadden, who's here tonight, and Rob Johnson. We're a small business that we take on some pretty interesting projects. Just got a kind of a sampling of some of the exciting stuff that we get to do. Our expertise is pretty broad. Geotechnical construction, tunneling, and water-related work. The our emphasis has always been to take an engineering technical approach to construction projects. We're not trying to do run-of-the-mill work. We're trying to do work that requires us to solve problems. You can see that in a wide range of these projects. I'm not going to talk in detail about any of them. And I'm also not going to use the 15 minutes of spiel. I'd rather get to the specific project here tonight.
I'm Kurt Breitenbucher, Brierley Associates. I was just asking Todd and Tom. They have been here in the Twin Cities about 10 years now. As they mentioned, I've been here about 7. We do a lot of the same things ECI does, but on the design or CM side. And once again, I won't go through all the pictures with you. We'll get to the presentation, but I just wanted to say it's great to see so many people out for the first one this year. So thank you, everyone. So the title is the Upper B Branch Restoration Railroad Sanitary Sewer Interceptor Crossing, which is quite a mouthful. If you want to go to the next slide, it was basically it's a project that was born out of a much larger emergency project. So the project team was ECI Brierley. ECI did the construction. We were their designer. The owners, the city of Dubuque. I didn't put up a map showing where Dubuque, Iowa is. The owner's engineer was Strand Associates. I've got to give Eric Veith a shout out. He was great for dealing with submittal review, dealing with the railroad, dealing with the owner. He was fantastic. So next slide, please. So the project background for this is basically, this is Dubuque. You can see here in the kind of clay color, this is the B Branch watershed. It all drains down here to a series of channels, and then this is the Mississippi River. Okay, no worries. So, starting in 1999, they started to have incredible flooding throughout the area. They've had 6 presidential disaster declarations. It's up to $70 million in damage. So over this multi-phase project, the portion that we were working on is these are the new flood control structures. There's a massive one here. There's a massive one down here. They had to eliminate a sanitary siphon that was over the top of it. So they essentially reversed the flow up and then crossed the railroad. And so that's what we did. We did a tunnel to replace that siphon essentially. It was about 310 feet of 48-inch steel casing pipe to house a 36-inch, was it Hobos?
It was Hobos, yes.
Hobos sanitary sewer interceptor. Next slide, please. So just some of the project constraints. Again, this is the same site, but now it's the aerial. So this is that one of those massive flood control structures that comes down through here, and then that other one is down here. The siphon would have been just through here. So we essentially reversed that flow, and the launching shaft, you generally want to tunnel uphill. So the launching shaft is going that way. So any sanitary flow will go that direction. So you can see the launching shaft, 310 feet, built by slurry microtunneling. This is the receiving shaft. The image I was able to find, it had just been backfilled, but you can get a feel for what it was right before they fully abandoned it. So on the west side, we had Garfield Avenue that we had to keep open. We had this Canadian Pacific Railroad or Kansas City Railway facility, and you can see we tunneled fairly close to it. Adjacent utilities, that's not uncommon. The railroad right away, and then on the other side, it was actually pretty wide open. The only thing we really had to do was, build a dirt road to get out to there. Next slide, please. So one of the things that Brierley Associates did was the contract documents required dewatering, regardless of if you used it. So we designed dewatering. It enabled the ultimate design that we went with, which was a shotcrete shaft rather than a more conventional shotcrete shaft. We had fine to medium grain sands, which is actually great for dewatering. The impermeable or a cutoff layer was another 35 to 70 feet below us. So there was no way to tow in. So we ultimately did 7 8-inch wells for the launching shaft and 4 8-inch wells for the receiving shaft. We spaced them evenly. ECI drilled them in with a rotary drilling rig. They had 310 GPM pumps, so at 80% efficiency in the lifting head that we needed. They were all running at about 248 gallons per minute. And when I checked in with Austin, the field superintendent, he said most of them were pretty much going full tilt. So unfortunately, my caption is wrong there, but this is a cross section of the dewatering plan for the launching shaft, just to give an idea of it. Next slide, please. So one of the benefits of design was we avoided railroad review for schedule. We utilized the required dewatering, and there's another slide where I can, you might be more familiar with, but if anybody here is familiar with the railroad shoring zones, the first line is, I believe it's zone A, second line is zone B. Zone A is you can do trench boxes, you can bench it, you can do whatever you want as long as it's safe. It's OSHA controlled in that location. If you cross into the other zone, you end up taking the full railroad surcharge. So by going with a tow-less design, and again, you can see that this is actually the contract design, we were able to move the excavations slightly closer together. And I believe we cut off about 55 feet of tunneling. We brought it closer together. Next slide, please. So again, BNSF, UPRR shoring guidelines. If you've ever dealt with them before, they typically, if you go into zone A, the one where you have to take the full surcharge, certain reviewers will make you treat it as a full distributed load for E80, which means if just the tip of your steel sheet piling goes in there, they say you have to put almost a 2 kip per linear foot, 2,000 PSF per linear, vertical distributed load on your shoring. So if you do it like real back of the napkin, every foot you go down where you need that, you might add a whole additional size of sheet pile that you would need to take that load. So we did this to get out of that shoring zone and to actually get closer to it without having a tow. The project had high groundwater, again, granular soils, no discernible cutoff layer. There was the potential here for sheet piles to not develop closure, to not have the interlocks lock up. None of the borings said cobbles and boulders, but it's the Midwest. You're right along the river. It could happen. Next slide, please. So some of the design considerations, there's different checks for shotcrete versus something like steel sheet piling. So what we did is in pre-construction, when they were just bidding it, we just did the real standard, ECI checks for shotcrete thickness with thrust, that sort of thing. Ultimately, when we did the final design, we checked it for buckling, treating it like a thin-walled cylinder. We did a RISA model, and for the unbalanced load, we used that to figure out the moment thrust interaction because of the unbalanced loading from the surcharges for like construction or a crane or something like that. As you can see here on the right, what we went with is a shotcrete shaft with lattice girders and welded wire mesh, and then at the bottom it was reinforced around the tunnel eyes. So at the top there, you can see what they did is they cast their footing for their fall protection, and then at the top there's a lattice girder just under that, and what they did is they pinned it back with soil nails so that they could excavate beneath it, because at that point there's nothing holding it up. The second one, they basically excavated down the next lift, put the lattice girder in, and then they flashed it in with shotcrete. And then because of the mesh and the shotcrete and the fact that lattice girders are pretty open in section, it just kind of stays supported that way. So you can see there, they're excavating down after the first lift. The lattice girders are primarily there just for form. If you're doing a shotcrete shaft like this, things are very good at taking up thrust as a cylinder, but if you make it unbalanced, if you get an uneven shape, something like that, it can really mess it up quickly. So they're just there for form. Basically what we did is we made it so that the lifts were such that they could go down to the next lattice girder, and if there was a construction joint or like a cold joint, it would be behind the lattice girder and not, say, in the middle of a span vertically.
So we'll shift a little bit of the conversation here. Just wanted to go through kind of a high level on slurry system microtunneling. I'm sure there's some of you here that have had some exposure to it, but it is a very unique tunneling method. Actually, and down at the bottom here, I'd encourage everybody to take a look at Ackerman's website. They've got some great visuals that really do provide a very good understanding of how the slurry microtunneling process works. The intent, they are a Minnesota-based company, which is fantastic. And obviously for us, it's great because these guys are local. If we want to ask them questions, run down and meet them in person. They'll run up to the cities and chat with people. So the intent of the slurry system tunneling, it's a closed face system. So shaft and the tunnel advances, tunnel and boring machine, and you have a jacking station here are the basic components. By sealed system, we mean that at the face you're actually applying with a bentonite slurry, you're applying pressure. So you're controlling your face. You essentially eliminate the potential for having any running material like you might have in an open tunneling system. The pressures that you use are obviously determined based on the soil properties you're encountering and the groundwater levels. Up in the top of the picture here, in addition to the tunneling equipment, there's slurry separation equipment. The slurry, it's a 20,000 gallon system, and that's necessary because you're constantly circulating a very large volume. And we've got a picture later on that shows a real picture of the slurry system. It's taking all the spoils that we're excavating at the front of the machine, and it's screening them off, pulling them out, so that slurry is getting reused, so that we don't have hundreds of thousands of gallons of waste material in addition to what's being excavated. On this project, I believe we ended up with a little over 30 yards of excavated material. So you kind of, obviously open cut is not an option when you're going under railroad, but you kind of visualize we're doing a over 300-foot long tunnel, almost 30 feet deep, and really a limited actual volume of soil that's being removed from the ground. Minimal disturbance is the goal with slurry system microtunneling. Go ahead, next slide. So this is a picture of the tunneling head. The cutter head here is custom configured based on the ground conditions that are expected. This is a soft ground cutter head. Ackerman also has somewhat standard, they have soft ground cutter heads, mixed ground cutter heads, and rock cutter heads. Within those, they can customize based on anticipated amounts of clay versus sand versus gravel, and then the types of rock that may be expected. There's two pieces. Microtunneling equipment is generally intended to be, as the name would imply, micro. It's intended to be as small as possible. It's typically used in urban environments. The site that we were on is pretty open for typical microtunneling. Microtunneling is used a lot in Chicago, on the East Coast, and on the West Coast. And it's becoming more popular in the Midwest as things get more developed. This is the lead section that has the cutter head and some of the hydraulic components for turning the cutter head. And then the second piece is the lubrication can or lube and jack can. They are mated up with a pressure seal as they're being installed from the launch shaft, and then come across to the other side. We've got a picture later that'll show what that looks like, and then they're taken apart in the reception shaft. The primary purpose there of having them be a two-piece system is that the reception shaft can be a lot smaller. Smaller shaft, less money. There's a note there. We'll talk about it some more, but the actual tunnel drive it took less than a week. Go ahead and next slide. So here's the start of the excavation. You can see we've got some interior dewatering going on. So we had the dewatering shafts, or the dewatering wells that were established around the perimeter. Those were drilled, and the dewatering was started approximately 2 weeks before the excavation was started to get an initial drawdown. We did have on the launch shaft, we did end up, Kurt had the note about equal spacing around the shaft. We did have some equipment staged at the backside of the shaft, and so we ended up with a slightly wider than Kurt's recommendation on the dewatering wells at that location. You can see that there was some water behind the track there, and so we did have to deal with some nuisance water as we were doing our excavation, because in that region where we had the equipment staged, we had a little bit of water moving. We were, I believe, about 8 feet farther apart than what Kurt's recommendations were based on his design, and we were pushing the limit, so we proved Kurt's design. That excavation method that we did use once we were deeper than what an excavator could reach is we actually had a mini excavator that was down in the bottom of the shaft, pulling material and loading into a muck box, which is not shown in the picture. You can go ahead and next slide. Do you want to do this one, Kurt? Talk about the settlement monitoring.
So in terms of the overall project schedule, they improved the project schedule by a month just for the tunneling portion. So I believe it was the 27th, the 28th of July, you guys started tunneling, and you were done like a week later. And then there was some other associated utility relocates, that sort of thing. You can see this was the original contract specified earth retention system. So there was all these, they aren't shown here, but there was a fiber optic on the other side. There was, you know, some aerial transitions, that sort of thing. So they ended up improving the timeline for that by about 2 months. They maintained traffic the entire time. The shotcrete shaft, I believe, on the launching side, which isn't shown here, there was overhead power right there. So it would have been kind of a nuisance to do sheet piling with a crane and a pile driver and all that anyway. Some of the incidental construction design, I say incidental, but it's still critical for a project like this. So we designed the thrust blocks. We did a settlement analysis for the railroad. We did the tunnel eye calculations, that sort of thing. We went and we did a whole parametric analysis for the settlement. We did, I think, 6 or 7 different methods. We compared them all based on workmanship and how much expected ground loss you could expect to see. And I'm happy to say that we were completely wrong there, because the railroad at this location's limit was about a ½ inch on the tracks. And we showed that it was like 0.37 is the worst we were expecting. And this is the settlement monitoring layout. I think the worst settlement we saw was like 0.04 inches. So incredibly good workmanship. The dewatering did what it was supposed to do. One of the things we did that was critical for that was we had the instrumentation specialist go out ahead of time. And the week prior to tunneling, what they did is they took a sort of normalization benchmark. So what they did is they went out in the morning, they took a shot, they went out in the evening and took a shot on all of these points. And then what they did is they calculated the average or that deviation between them and set that as their baseline. Like I said, this work was done late July, early August in Iowa. So during the day, you can be up over 100. At night, you can be much cooler than that. The railroad was requiring that the shots actually be on the rails themselves, not on like the ties or the sleepers. So the thermal expansion, you can get a rail that will move by like ½ an inch just from the sun being on it, or versus being in the shade. So what we wanted them to have was a baseline that showed how this rail could move without any tunneling at all. So next slide, please. Do you want to take this one?
Okay, so one of the big challenges that we looked at was, as this tunneling head is advanced, then you follow it behind with a casing pipe. Eventually, the product pipe, the Hobos, is installed inside of the casing pipe. There's a few different ways of attaching the casing pipe to each other. There's a push joint. Industry standard is the Permalock joint. There's also one made by Trilock. An alternative is to do a traditional welded joint. What we ended up finding out was that even though it wasn't in the contract specifications, CP rail was going to require, even if we used a push joint like Permalock, they were also going to require us to put a seal weld on it. If we're setting up to weld it, we might as well weld it. So we ended up going with welded joints. The pipe is specifically sized to go with the tunneling head. The engineer, Strand Associates, and their tunneling consultant had worked with the railroad and established an allowable overcut, which was 1 inch. And that is the overcut between the actual excavated diameter and the diameter of our pipe. So 1 inch on a diameter, 1/2 inch on radius is extremely tight. That's where the lubrication system that we use becomes essential. And that's bentonite with some polymer additives to make sure that our jacking forces don't get excessive, especially in sand conditions like we were in. And I think later on we have a slide that kind of talks about some of those jacking forces. The one important note about these systems is it's really critical that the designer, being the owner's engineer, establishes minimum and maximum allowable diameters and doesn't try to get too prescriptive, because there's only so many of these machines and they're very expensive. And you allow the contractors to size the pipe based on what their machine is. If you become prescriptive on what the pipe size has to be, then the machine has to match it. And all of a sudden you're buying a $1.5 million machine for your project. You get excessively costly on most microtunneling jobs. Next slide, please. Okay, so this is success on the other end. One note that we haven't talked about yet, you'll see here, you'd seen previously a seal that I didn't talk about, that we have a seal on the launch side and a seal on the reception side. We actually didn't need the seal on the reception side because we had done some pre-excavation grouting that was successful in controlling any running sands, and then the dewatering in combination with that was successful, so that we didn't have water intrusion and we didn't have soil coming in. There was slight misalignment, which is goes into lessons learned. We were off horizontally on our layout by approximately 6 inches. You can kind of see it in this picture, but that could become a very critical and costly mistake if you don't have. In this case, we were able to successfully do that pre-excavation grouting and the dewatering. If we didn't have that, obviously that seal becomes much more critical.
Standard in those seals, how much deviation?
The seals are typically designed for 2 inches of deviation. They can be designed for more, but your pit size gets a lot larger if you design them that way, which adds cost. Here's the note about some of the field adjustments in the wells and the effect on water levels. Yeah, it was a surveyor. Yep. Go ahead, next slide. Slurry separation plant there on the left side of the screen. It looks like in that picture, they're doing a pretty good job of keeping things cleaned up. You'll see kind of 3 ramps coming down off of the top. So there's actually screens and a shaker. Pulls the solids off on 3 different screen sizes, and they get deposited below, and just use a standard skid steer to remove those piles as it's coming off, and then the slurry gets circulated back through. Here in the white pump is a slurry circulation pump, booster pump. It's actually lifting it up the shaft wall, and on the line on the right next to that white pump would be coming down, and then the back side of the jacking frame has a keyhole that pipe as well as personnel can get inside of the pipe. Go ahead, next slide. Here's a couple of pictures showing the on the left here, the pipe is prepped for welding. You can kind of see in the picture how it's nice and cleaned up. And then on the right here, this is pipe being welded. 48-inch diameter pipe. Advantage there, as opposed to any smaller of a pipe, is you can you can have 2 welders going. You're able to control temperatures and not overheat and affect each other. Next slide. So pipe all the way across, and this picture is the Hobos jacking pipe being installed. The total duration ended up being 5.5 days. To microtunnel. We do run a 24-hour operation when we're doing the tunneling. The biggest reason is that we're avoiding any surcharges in jacking forces from any sort of collapsing soils that we could encounter. We can do our best to maintain that pressure on the annulus through some ports that are installed in the jacking pipe. However, it's the best insurance is to just keep tunneling, and then you're in complete control. Go ahead, next slide. Back 1 slide.
For those white pipes.
Yeah, so white pipe is the larger white pipe is actually a 4-inch pipe, and that was actually a fiber optic line. That was intended to be a directionally drilled fiber optic line. We hired a directional drilling sub. They had issues with their launch and their launch angles that the railroad was allowing us to use for the HDD. And so they were breaking the HDP pipe. So we ended up making a change, abandoning those lines that they had tried to install by HDD. And we attached a 4-inch line to the outside of the Hobos pipe. So it was actually housed between the casing pipe and the Hobos. The other PVC pipe is the grout line for the annulus between the Hobos pipe and the casing. Fill that 1 shot. We did fill it in 1 shot. Yep. That really ends up. There's 2 factors there. One is heat, controlling the heat of hydration on that annulus. The other is making sure the bulkheads and the hose pipe the product pipe are designed to be able to handle the loads. Obviously here it wasn't an issue because it's a small pipe. This is machine pulled out of the shaft. We did not encounter any. Kurt mentioned this was a good drive. We did not encounter any boulders, cobbles. The head was in pretty good condition when it came out. That the head can, depending on the materials you do encounter, the head can get pretty beat up during the drive. Slide says questions. I think that means it's open.
What do you do? You do it on a boulder then.
If we expect boulders, absolutely. So question is, what if we do encounter boulders, cobbles, obstructions? So if we're expecting any, even outside chance of it, we'll put what are called disc cutters on the head. So that would be a mixed ground head. Those disc cutters will actually cut through the boulder obstruction. And those are, we rely on the geotech report for any anticipated materials in there. Those disc cutters will be designed based on the expected compressive strength of rock. If we did encounter one in this case, there's a couple options. One is that technically these systems have face access. It's almost impossible to do. You would have to effectively dewater at the location you're at. So if you're in the middle of that alignment, not very feasible. The other option then is to either put down a rescue shaft, which again, in this case would not be an option. The only other option is to either oversleeve with a larger casing pipe, or from the launch shaft, or to do a second tunnel from the other side. So there are no good options, is the answer.
Like you put those papers on there.
Yeah, so exactly, if there's any chance of now, the picks that we use, we call it a soft ground head, but we do have 800 tons of jacking force. So if it's a boulder or cobble, anything that's roughly the size of the head, we'll actually typically be able to just push that with us the entire way. And then we have to deal with the problem at the reception shaft. If it's a smaller boulder than what the tunneling head is, a lot of times we'll be able to just, eventually it'll get pushed off to the side. The real problem would be if we run into some obstruction that's larger than the machine, and our 800 tons of jacking force isn't able to push through it. Again, I know there's some individuals in the room that like to hear the importance of the geotech report early on. That's identifying this.
Very important.
Yeah.
What was the railroad's requirements for inspection or emergency response, or what? Having special requirements, should you have an inspector on site or anything like that?
Yeah, so question is about the railroad requirements related to inspection. In this case, the railroad had hired their own independent consultants, both for review of our submittals, which was a bit of a challenge. Brierley did a great job of working through it. They initially were not going to be doing a review, and halfway through our job, CP became CPKC, and then they decided that they were going to review it. So Brierley did a fantastic job of reacting to that and being able to answer all of the questions. I believe HDR was the railroad's engineer. They did have people on site, although the folks that were the on-site inspectors had no previous microtunneling experience. So they really did rely on some of our early involvement meetings that Brierley attended to make HDR's tunneling engineers comfortable with our approach. Yeah. Question is, was ECI design build contractor? Yes, in that Strand had specified tunneling. They did specify microtunneling, or did they just specify tunneling?
They specified microtunnel.
They specified microtunneling, and they specified, obviously, that shafts had to be constructed. That was kind of the extent of what their design. There was some ancillary pieces. There was some open cut pipe that we had to do to tie in. But the bulk of the project was the shafts and the microtunnel, and there was no design put into those. So it was a design. It was a design bid build. Formally, it was design bid build, but for all intents and purposes, there was a lot of pages that said contractor sign. So
You help contract and.
correct,
Brierley.
correct.
What was the maximum that was you apply from going from LA? I'm considering that especially after this unfinished do you think that actually help you guys going the time?
Yeah. So question is two-part question. One is the maximum jacking force, and the second is the limited overcut and whether or not that helped. Maximum jacking force was just over 80 tons. Kurt maybe remembers off the top of his head what the calculated jacking force was. It was a lot more than that.
We calculated that it would be like 300 tons, and I think that frame can do 900.
The frame can do 800.
Okay.
Is rated for 800. It can do more. We've tried it. Got to see what it can do, right? Yeah. So the jacking force that we actually saw was only 80 tons. The single biggest piece there was that we did a 24-hour operation. That obviously comes with a cost to do that. We have to have 2 qualified crews down there. People can't work 24 hours straight for an extended period of time. And the other piece that limited annulus, yeah, that keeping that minimized does allow us to, the bigger that annulus gets, the more pressure, no pun intended, is put on the criticality of the design of that slurry. And Brierley did help us out with some of the design elements on that slurry for the different additives that we used.
What is the external lubrication system that goes along ways towards?
Correct. Yeah, the question is about the external lubrication. It's critical in reducing those jacking forces, or in this case, really almost eliminating the jacking forces altogether. Yeah. So frequency of trains during tunneling. So that was a big concern of ours, because CP had a requirement that we actually stop tunneling if we were under anywhere under the tracks and there was a train. We fought pretty hard to get that requirement waived. Brierley helped us in that argument, saying that it's in our best interest to keep going. The worst thing that you can do if you have ground that is starting to move is to just sit, get past it, get the casing that's intended to hold the ground installed through that zone. They wouldn't waive that requirement. We only had one stoppage of about 2 hours during the actual tunneling. So that ended up being a benefit. Now, we did have some pretty big challenges in the lead up, because actually on the slide where we had all the settlement monitoring points, when we went out to do the settlement monitoring points, they had trains parked all over the place. And the railroad would not allow us to install the targets if there was a train on the track. Even if it was parked and we had a watchman there and you could physically reach down and put the target on, they wouldn't let us reach down under the train. So we had to wait until the train moved, and then the train would move, and we'd call the surveyors and, hey, come on quick. And then another train would come and we'd look at it. And, so we ended up, it was quite a long process for getting all those installed, and they had requirements. Well, Brierley had, their recommendations on how long we established for a period beforehand, and there were some contractual requirements for having a baseline. And so we were within a couple days of our planned start of tunneling to when we actually got our targets on, and we were able to get everything approved, which has large impacts because all the equipment you see, it is not cheap. And if we would have to sit and wait for a train to move so that we can put a target on a track, not desirable, but we didn't end up running into that issue. So
How would the process be different than the site of clay instead of sand? What would it have been different?
yeah, so question is, how would the process be different for clays instead of sands? Depending on the clays, right? The lubrication can be less critical if the clays will somewhat support themselves. Another piece that that I didn't touch on in sands is that depending on the amount of fines that you have in the sands, you can actually start to lose some of your slurry out into the formation. And that's something that our quality engineers on site are keeping a constant track on the volume in the plant to make sure that we're not losing any out into the formation. So on a whole, that clay ground is typically a little easier to tunnel in. Yeah.
What was the dewatering failure? You guys have a response plan and dewatering, like, in terms of shaft. Your shaft was open while you were building it. You're dewatering, you expect it time to fix it and stuff like that. In general, what was your excavation ground, like dewatering failure?
Yeah. So question is dewatering and potential for dewatering failure and response time on that. So we did have the shaft itself is kind of a way to monitor the dewatering, obviously. And then we did have piezometers outside that we were using to monitor those water levels. We did, as I mentioned in that picture, there was water that nuisance water as we were going down. And when we did get right down to the bottom, kind of the last 5 feet, we did really have a lot of work to do in establishing ourselves at that face where we had a wider space between the dewatering wells. We had to put in a few extra sumps. There weren't any contractual requirements during excavation specific to dewatering failures. And then for during the tunneling phase, we had some large sumps established in the bottom of the launch and reception shaft that, if needed, we could dewater from.
It was a 24-hour operation. Wasn't any certified and unmonitored loss of power or something?
Correct. Yep.
And these were what, 2 or 3 phase electric pumps. So there's a much smaller chance that an electric system goes down than I've been on many projects where you have the diesel or the gas ones, and those require, like you said, a tender all night for them. The ugly contingency for this, because it was down in a floodplain, would have been if there had been, say, a flood event, they would have probably flooded the shafts, and you guys probably would have stripped the electrical equipment from the machine, waited till it was over, and just kept going. But luckily, that did not happen. So.
Yeah, correct. Like Kurt said, we were definitely in the floodplain, and we were close enough to the Mississippi River that there were some there was residual influence on that groundwater from the Mississippi River. We didn't have any issues with it during the time we were on site, but that was a scenario that we had evaluated early on with Brierley, and we determined that likelihood of it happening based on the season that we're going to be there, and then as Kurt said, the response plan justified the means and methods that we were using.
Are there any ground monitoring requirements besides surface monitoring reports like extensometers, micrometers, things like that?
Yeah, so Kurt can probably talk that. Should tell these guys, huh? The question was about any ground monitoring requirements other than the surface monitoring points. Kurt hasn't answered any questions yet, so I'm gonna make him answer this one.
Could you tab back to the one with the settlement monitoring points? So unfortunately, I snipped it off, but just above this, these three blue points were essentially an extensometer. They weren't a fancy one. They basically took, a standard UMP, a telltale, but they just buried it in the ground. So they just sank a casing. They put down, I think it was steel pipe with washers welded on it, and then drove that down into the ground. And then, so the casing could move freely from it. If anybody isn't familiar, when people typically do like settlement calcs for these, what most people are concerned about as the tunnel, as you get surface expression of most settlement, you get like a trough around it, right? That goes out from either side. You get a trough here and a trough here. But what happens during construction is as the machine ingests material, you get, say, a couple face diameters ahead of it, a trough that's coming into the face. And so, especially with something like this, where you have a little bit of a longer lead up to the railroad tracks, you would want points like that, like an extensometer, so that you could tell if you did have a settlement issue before you get to the tracks. Luckily for us, even these that were only 5 feet above the tunnel horizon barely showed any movement.
What do you have to do if you have 2 months settlement?
So that actually was the primary question that the railroad was concerned with. And to our surprise, really the solution that they were happy with was that we have a couple of loads of ballast rock on site, and we have a loader and a guy that's willing to put the ballast rock under the tracks. And we're like, yeah, we can do that. We got it. So that was actually, we kind of thought that was going to be, because they started asking those questions, and we're like, what, I'm asking Kurt, I'm like, what are we going to say to them? I don't know. And they were happy with that answer. So yeah, the railroad actually ended up, all things considered, was very good to work with.
So you guys lift the guys into the rock. If we had some, they said you guys
They would have called out a rail crew to assist with lifting the ties, correct? Yep.
What were the shaft sizes in your 24-hour day?
Yeah, so question was the 2 shaft sizes. Launch shaft for a 20-foot pipe, which is what we were jacking. The minimum is 34-foot diameter. So that's what we had. And the reception was a 20-foot diameter, which is a little bit more than the minimum, but it gave us enough space to work. And the second question was,
Your 24-hour day as well. Explanation. There's the pipe. That's proprietary.
you're asking how many we were getting in a 24-hour shift? So it took us about an hour to push a pipe, to actually tunnel the pipe, and then between loading it in, prepping, welding, all of those things, and then I think if you go ahead a couple of slides, and I hope I'm going the right way. Go one. Yeah, so I guess we don't really show it in any of the, go back one if you would, please. So you can kind of see it here. It's tough to see there. And there's a bucket in the way. But there's 2 slurry lines, 6-inch slurry lines. There's some electrical lines and some hydraulic lines that are actually contained inside, and those are obviously temporary. You know, just doing all the hookups and installations for those, that process ends up taking between 3 and 5 hours per pipe. So that's actually the longest part. The tunneling itself is the fast part.
310, and they did it in 5 days.
5 days, okay, I got it.
But to,
so between welding and doing all the hookups was between 3 and 5 hours.
could you go forward like 1 slide? So to Sam's point, when that pipe gets flown in, all your utilities that are in there that you need to make the machine out there work are sitting inside the pipe as it's flown in. They set it in the cradle, and then somebody has to go through this little keyhole and hook everything up. And if you've ever dealt with, say, like shotcrete hose or pressure hose, that's hard enough to manhandle, like just out on the open ground. So imagine getting it through that little hole and then get everything hooked up. And you have to make sure as this process goes on that it's all correct the entire length. So.
One issue that we did not run into on this job that we've had in the past is sometimes stuff happens, and we actually had slurry lines blow apart while we were tunneling, like up at the tunneling head. So we would have to have guys march in 600 feet, and you can picture what marching is when you're in a 48-inch pipe. It's not marching. You're crawling in 600 feet, and then you're actually, you know, digging through a foot of slurry to get to the pipe to replace the gaskets and the seals on those pipes. So there's this one was a very, very, very successful tunnel that didn't have the normal challenges that we do encounter.
This is why they always make sure they have like a really short person on the crew. So
Yeah.
Questions, how long does it take to excavate and do the shotcrete for each, say, like either the access, caps, that, what was their vertical lift height?
So the 2 questions are vertical lift height on the shotcrete shafts, and then the duration. So vertical lift height was 5 feet, and the duration was roughly 3 days per cycle. And the 5 feet required that pre-excavation grouting, because your 5 feet as you're excavating down is more than the OSHA allowable. Overall verticality was 30 feet, roughly
25
feet. With our 25 to the invert, but we had to go a little lower. But yeah.
You guys have a seal for the bottom?
We did have a mud slab that we were working on.
The gun condition and I on that room, and most of the small animals in the over tire plant. So you have to like comfort nothing, so that's more boy.
Yeah, so question is about contact routing. Yeah, I don't think this is working anymore, is it? Still working? I think it's off. Okay, so so we did 2 pieces of grouting. The first is what we would call the contact grouting outside of the casing. And that's where we also use the same ports or holes for pumping the lubrication to keep that annulus during jacking. After the jacking is complete and you strip the casing out, then you go back into those same ports and pump a contact grout, which is a cementitious grout. you're essentially forcing your bentonite out of the annulus and putting a cementitious grout that'll cure out in that space. Then we also had the annular grouting, which is between the Hobos pipe and the casing pipe. And that was the picture you see here with the smaller white PVC pipe.
Does that happen where you force the bentonite out of the annulus? Is that completely through the tunnel, or is that at a certain stage of the tunnel process?
Yeah, so the question is about when the contact grouting piece happens. So there was a requirement in the spec that said that I think it had to be either 48 or 72 hours after the casing pipe was jacked. Now, it was somewhat a technicality that we had to work through with the owner's engineer and the railroad, because you have to maintain, you can't pump that contact grout because it's cementitious until you're done pushing. As soon as you pump that, you're essentially locking that pipe in place. Now, with 800 tons, Kurt could tell me the math. I think we could probably push it still, even with a cementitious grout. But yeah, the intent is actually that you would do that after you're complete with your jacking. The other piece that they gave us some leniency on was they had the 48-hour requirement, but practically, if we haven't seen that ground loss as we were tunneling, the preferred method is to be able to strip the tunnel of all the utilities first and then go in and do the contact grouting, as opposed to having to try and work over the top of all the utilities. And
So I got a question. You were saying something early slide about it didn't have railroad review.
Yeah.
Scroll to like slide.
Well, that was the intent.
So why didn't it require railroad review?
Well, so we didn't cross into. It's this one. We didn't cross into any of their shoring zones. So again, this is the contract design, and I don't believe it was sealed because it's essentially it's contractor's design. So if we had taken this design, and keep in mind, we have high groundwater, we have granular material, we have no discernible cutoff zone, no clay, no rock, no anything. So if we had taken this design, and maybe they fully vetted it, we didn't check their design. But if we had said, okay, let's check the embedment. So now maybe this is the required structural embedment, just moment equilibrium for the soil pressure, right? But then we have to cut off the groundwater. So the way you do that in granular material is you carry it further down or you dewater. Then you have to add your factor of safety, all of that. So if we had carried the sheeting down into that zone A, it immediately goes to their full structural review.
Gotcha. So because of the shaft designs, alleviated that issue.
Yes.
Okay.
And you were asking about a seal slab. So they put down a seal slab just to have a nice working surface, right? But if we had done this and we hadn't carried it down further to eliminate piping or any of that, we might have had to do a big jet grout or tremmed base plug, that sort of thing. And that's incredibly expensive. So
When we were running, we were doing the dewatering check, what kind of dewatering where we did, was that an adder to the 24/7? Or was that part of the 24, or was that putting us over that half inch? It included dewatering,
So that was one of the things we went back and forth with the railroad on. There's kind of this conventional thought that if it's really good granular soil, you don't get dewatering induced settlement. You're taking away the pore pressure, so you do get some amount of the skeleton of the soil is now taking up the stress, but it's not like a clay or a fine-grained material where when you take away the water, you start essentially consolidation settlement. So the railroad was concerned with from the launching shaft out to the first track, it was about 74 feet. So what they wanted us to do was calculate the tunneling induced settlement. And then if we had dewatering induced settlement, they wanted us to have it be additive. And we went back and forth with them and we got their buy-in that there wouldn't really be any. Again, the Mississippi River is probably only half a mile to, well, north was all messed up on these drawings. Would be about a half a mile this way. So we didn't necessarily draw down the water. What we did is we did use, the standard Powers construction dewatering method. We designed it as a system of wells such that the curve would put the water below the base of excavation, right? But what these wells were really doing is they were just intercepting the water. The reason those pumps were so big is we didn't have a million tiny well points out there with a header system on them. These were just big, 310 GPM pumps running nonstop so that any water would come into the wells. And keep in mind, they were 8-inch, so they're pretty big wells. And they had, like 4 inches of filter pack around the outside.
3-inch radial.
So they were almost like a 12-inch well. So we weren't really trying to draw down the water because we didn't feel that would even be possible with the proximity to the Mississippi. So
out of your 0.3, if one was gonna settle, how much was dewatering? 0.
sorry, what?
You told the railroad was gonna settle the third of an inch, yeah.
Just from the tunneling,
Dewater,
we said 0.
0.
All right, well, thanks very much to Kurt and Sam for